In this video, we're going to talk about how to find the slope of a parametric curve, slope being dy dx. And this concept is something that we actually did talk about before, that dy dx is the same as dy dt over dx dt. Important information to us because parametric functions are given in terms of t, where the parameters are based on x and y. So we have x is defined as t squared plus 9. So x prime or dx dt is going to be 2t plus 9. 2t plus 0, right? Derivative constant is that. And again, it's just kind of like implicit differentiation. So when I take the derivative of this with respect to t, we get dy dt on the left side. And when I take the derivative of the right side, we just do the power rule here, and we get 20 t to the fourth minus 18 t to the second, again plus 0. So dy dx is essentially this expression divided by this expression. So I can write it as 20t to the fourth minus 18t squared all over 2t. And I could leave my answer like that, which is perfectly fine. However, since the next question is asking us to find the second derivative, we are going to simplify this because it makes it a little bit easier. So if I can simplify this, I can reduce by dividing each of these terms by 2t. So we get 10t to the third minus 9t to the first. This way, when I do find the second derivative, I don't have to worry about the quotient rule. The thing that we do have to be careful about is how the second derivative works here. So if I take the derivative, I want dy, d2y, dx2. So I'm taking the derivative of this. All right, I'll write it out again. 10t cubed minus 9t. And if I do this and I want the second derivative, or d2y dx2, I'm taking the derivative of this with respect to x. But we have an issue with that, right? Now I'm going to have to worry about implicit differentiation. So essentially what happens here is if I follow the power rule here, we get 30t squared, again, times dt dx minus 9, and then that would be times dt dx. So I could actually just say it is this times dt dx, right? That's just implicit differentiation. But I don't like having this dt dx lingering off, right? So this is d2y dx 2, or d squared y dx squared. So to take care of this, well, this is just the reciprocal of dx dt, right? So if dx dt is 2t, dt dx is equal to 1 over 2t. So that now I could actually write this as 30t squared minus 9 times 1 over 2t, or divided by 2t, and that's where this expression is coming from. So let's go ahead and try that again. All right, let me just write the notation. D squared y dx squared. Given the parametric equation, x equals 5 sine t and y equals 3 cos t, find an equation of the tangent line to the curve at the point where t is equal to 2 pi thirds. So we want to know, we essentially need this little formula, y minus y1 equals n times x minus x1. So to find y1 and x1, we just plug in 2 pi thirds into the original parameters. So if we do 5 times the sine of 2 pi thirds, that is going to be, let's see, we got a line minus 5 times the sine of 2 pi thirds, 5 radical 3 over 2. And if I plug in 2 pi thirds into this one, 3 times the cosine of 2 pi thirds is going to be 3 times negative half. So that's going to be positive, or sorry, negative 3 halves. So y minus negative 3 halves, you can write as y plus 3 halves. Okay, now we need to know dy dx, so we need dy dt. And so dy dt is negative 3 sine t. Dx dt is 5 cosine of t. And so dy dx is negative 3 sine of t over 5 cosine of t. And so then dy dx at t equals 2 pi thirds. And then it's just going back to the basic trig we were just doing. So the numerator is going to be negative 3 times radical 3 over 2. So negative 3 radical 3 over 2. And the denominator is going to be 5 times negative a half. So negative 5 halves. And since the denominators are the same there and they're both negative, I could actually just write it as negative 3 radical 3 over negative 5. And then again, those both be now positive. So I can actually replace my slope here and say that my answer is y plus 3 halves equals 3 radical 3 over 5 times x minus 5 radical 3 over 2. Okay. Next one, find all points of horizontal and vertical tangency given the parametric equations. So we need to know when is dy dx equal to 0 and when is dy dx going to be undefined, or where's the denominator going to be 0. So again, we'll find dy dt, which is going to be 2t minus 8, and dx dt is going to be 6t minus 6. And so dy dx is going to be 2t minus 8 over 6t minus 6. And I could simplify if I wanted to by factoring. I'm not going to worry about it right now. But we need to say, okay, so it's horizontal if the numerator is 0. So 2t minus 8 equals 0. So that's going to be when t is equal to 4. And it is vertical when the denominator is equal to 0. So that's 6t minus 6 is 0. So t is equal to 1. And so the points, all points of horizontal and vertical tangencies are going to be the x and y coordinates. So if I plug in x of 4, we get 3 times 4 squared minus 6 times 4, and y4 is going to be 4 squared minus 8 times 4 plus 9. And we could simplify those, which I'm going to do in a second. I'm also going to find the vertical by doing x of 1 and y of 1. So x of 1, y of 1 is going to be a little bit easier in terms of mental math. So 3 times 1 squared minus 6 times 1, and 1 squared minus 8 times 1 plus 9. So here I filled in these, and so our coordinates would be 24, comma, -7, and -3, comma 2. So here you can see I actually put this into the calculator. Just to show you real quick how we did that. If you go to menu, on a graph page menu, graph entry / edit, and then we have parametric as an option. So I went ahead and typed in my parametric function. You can see it is my x and y parameters. It's only graphing it from 0 to 6.28. I guess it's obviously thinking that we're going to be dealing with trig when we type it in. We could extend that further if I wanted to. I'm not actually going to worry too much about that. And let's see. So now that I've got the graph here, and the other thing I can take a look at is if I go to menu, trace, graph trace, it actually steps along the graph. You can see here it's stepping and telling me what's happening at t equals 0.7, 0.8, 0.9, 1.0. We had -3, 2 as one of our answers. So you can see that at t equals 1, -3, 2, and you can see the graph even looks vertical there. So we want to step out to where t was equal to 4. And actually, I bet if I type in just the number 4, it'll go to t equals 4, and it even shows me the coordinates there as 24, comma, -7. And we have t equals 4. Graph looks pretty horizontal there. Curious to see if the calculator can handle dy dx on a parametric. We'll just look real quick. And if I try to hover over, it's not letting me do it. So again, we just have to use our eyeballs to estimate what's going on there, but it wasn't too bad. All right, that's where I'm going to leave off.